All right, so we got the 6.1 part 2 notes. Yesterday was just the graphs. Today is actually dealing with the equations. First off, we have exponential growth. Looks like that guy. And not that it matters, but the mom function for exponential growth was a times b to the x. Well, this one looks a lot like it. We use a slightly different form. The amount after time passes, a sub t, is the principal times 1 plus the rate of growth to the t. And a sub t is literally, I'll switch over to typing for you, the amount after time passes. That's all it is. The amount after time passes. R is for the rate. It's the rate of growth. And it is expressed as a decimal. Must be a decimal, okay? Or a whole number, but it's never percent. T stands for time. And this 1 plus R piece is something they call the growth factor. All right, so there's the equation. Let's use the equation. Pause it if you got to. We also have exponential decay. An exponential decay would be something that starts high and works its way low. You have a very similar equation. The amount after time passes is the principal times 1 minus r to the t. It's going to decay, so we're going to be taking away from 1. The 1 is there because it represents 100% of something. That's what it represents. So again, for your notes here, a sub t is the amount after time passes. R is literally the rate of decay. And again, it is expressed as a decimal. And then 1 minus r would be what we call the decay factor. All right, so there's 2 pages of basically notes. Time to do a problem. The population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% annually for the next 4 years. What exponential model? What exponential function models the population of the city over that 4-year period? And you're just going to use this guy here. Now, when you take this 1.3%, we're going to convert to a decimal. And this is a skill that just a lot of kids can't do. All you do is you move the decimal 2 places left. So 1 and then 2. All right. So it becomes r equals 0.013. And let's plug in our form. The amount after time passes is the principal, which is at 4.6 million, the initial amount, times 1 plus 0.013 to some time frame. Now obviously clean this up. You can figure out what 1 plus 0.013 is. And this is the amount that this city will have after some time passes. All right, if the population continues to grow at the same rate, what will the population be in 2040? So our data starts in 2010, so the time that passes is 2040 minus 2010, which is 30 years. And we're just going to take that 30 years and we're going to throw it right there. So the amount in 30 is 4.6 times 1.013 to the 30th power. And it's going to be a gigantic number. I guess I could sit down and do it by hand, but that'd be a huge waste of time now, wouldn't it? So let's see what the TI-84 says. Most of you guys are probably pausing the video and just writing down what you see, that you're the problem. So 6.77. Now I'm going to write down this whole decimal because I have to convert this to millions, right? 6.77. What else we got? 0.57. And after that 7 is an 8. 0.58. That is millions. So let's move that decimal. 6,770,058 written properly. There you go. City grew quite a bit. A car was purchased for $24,000. The function y equals 24 times 0.8 to the x can be used to model the value of the car. X years after it was purchased, does the function represent growth or decay? Well, it's kind of written in that form I was telling you about. This is your principal, and this is the 1 minus r to the t piece. And this is decay. It is multiplying by 8/10 as you move right, so it is decaying. This is decay. We are multiplying by 0.8 as we move right. Now, what is the decay factor? The 1 minus r piece is the decay factor. You'll notice it lines up with 8/10. So the decay factor is 0.8. What is the rate of decay? Well, in our original decay function, we line that up with 1 minus r. So 1 minus r equals 8/10. And then we have a simple two-step equation. Now, if we take away 1 from both sides, negative r equals negative 0.2. And then we divide out that negativity. The rate of decay is 0.2, or 20% decay rate. It is decaying by 20%, because if you multiply something by 8/10, you're keeping 2/10 of it. Or sorry, you're losing 2/10 of it. Graph the function on a reasonable domain. What do the y-intercepts and asymptote represent? What will the value of the car be? When will the value of the car be about $5,000? So a reasonable domain for this would be that the lowest time is 0. You're talking about time, it'd be 0 to some high number, all right? Let's say 20 years. 20 years is a long time to keep a car. But you can make up any number you want, but you have to start at 0. I'm going to let my TI-84 do this one for me. Original equation was 24, and it was thousands, but we're not going to put that. 0.8 to the x. And let's just set that x min to be 0. Let's set that x max to be 20. We'll have to play with the y max. I don't know why. I mean, I knew what it was going to be. It was going to be 24. Let's see here. It doesn't make sense for a value of the car to ever hit 0. It's always worth something, even if it's scrap metal. So let's set a y min of 0 and a y max of 24. A very reasonable graph. So anyways, talking about the time there. We're talking about the amount of time, your range. This is domain. This is range. The highest amount is going to be 24, and the lowest amount is going to be 0, and it's in thousands, okay? There's your graph. Now, when will the value of the car be about 5,000? So let's think about what we'd be doing on paper. We're not doing this by paper yet. Maybe we can, I don't know. We would say that 5,000 is equal to 24 times 0.8 to the x. And now we're not doing this by hand yet because you don't have the ability to do it by hand yet. We're going to let this be y1, or we're going to let this be y2, or maybe vice versa, because I think I already have that in as y1. But I don't need thousands there either because this is in thousands. I just need a 5 equals. I also need my technology to work. Go to y equals, put a 5 in y2. I've already got a perfectly good window. Hit the graph key and you should be playing along. That's a hard thing for some of y'all to do. Second, trace 5, enter, enter, enter. So 7.03 years. There you go. All right, what rate of yearly interest is required to turn a $100 investment into a $1,000 investment in 5 years? So I'm obviously going to be growing. So I'm thinking about my formula for exponential decay. And I start with 100 and I become 1,000. It's 1,000 equals 100 times 1 plus r to the t to the 5th power. And this is a very doable question by hand. We're going to divide both sides by 100. 1,000 divided by 100 is 10. So 10 is equal to 1 plus some rate of interest to the 5th power. Now, before we left for Christmas break, we were learning how to counteract a 5th power. And you counteract a 5th power, you raise it to the 1/5 power. The opposite of any power is its reciprocal. So let's see what 10 to the 1/5 is. By the way, remember, you can do this in Desmos if you don't have a calculator. You can go to Desmos, type in 10 to the 1/5. It'll work beautifully. It's 1.5849. And that is now equal to 1 plus r. And all we have to do is move that 1 over. So 0.5849 is r. And if I like percentages, the rate is 58.49% per year, which is impressive. Impressive. You'd be a millionaire before you even knew it. Because, the next year you'd have $1,600, and then the year after that you'd have quite a bit more. You'd be almost $3,000 by then. And it would grow really, really quick. Same question, but the monthly rate. So 5 years is 5 times 12, 60 months. So this thing's going to start off an awful lot the same. We want 1,000. We start with 100. But this time, the time frame is not 5, it's 60. So a lot of the same steps. We divide out the 100. And then we have 1 plus r to the 60th. And the opposite of the 60th power has to be the 1/60th power. And we're going to take away 1. Now this time I just went out on paper. You don't have to go straight to a calculator. Doesn't do you any good. But this would be the monthly interest rate. And it's 0.0391. Which as a percent is 3.91%. And that's per month. It's monthly. Which is really, really, really good rate of return. Well, what do I know? I'm just a broke math teacher. All right, what if the rate of growth or decay isn't happening over a singular time period? Now, I say that because I was talking like we had questions like that were per year or per month. This one's a little bit different. A certain city doubles in size every 11 years. If this trend continues, what will the city's population be 100 years from now if the current population is 220? So the first question I have there is, why can't I just double it till 100 years have passed? And that's simple. 11 does not enter 100. Nicely in rows. So that's the issue. So I modify an existing idea And there is no formal letter for this, but there's the original equation for growth. And we're going to put that time over what I call TP, which is the time period, or the time per. Here it'd be 11. All right. Now, by the way, if I double, what is my rate of growth? And that's the issue. What is my rate of growth? It's not 200%. R is 100%. Now, I weigh about 215 right now. If I doubled my weight, I would add 100% of what I am. I wouldn't add 200% of what I am. And 100% as a decimal is 1. So you're going to see the number you want for doubling to show up. So the amount after time is the principal, which is 220, times 1 plus that 1 to some time over the time period it takes to double, which is 11 years. I know that when I asked that question, some of you were actually listening, were like, oh, your rate of growth is going to be 2. No, your rate of growth is 100%. But the 2 you're expecting does show up. So here's my equation. And this is an equation that I can simply plug a number into to finally get the result. I wanted to know what the population will be 100 years from now. I can feed that thing a 100. And I'll have it. And it's going to be quite large. 220, 2 in parentheses, and the exponent's 100 divided by 11. So 119,967. The reason I'm rounding like that is because there's no such thing as 2/10 of a person. Life forms get rounded up. 119,967. We round life up. We don't say 0.2 on a life form. We round it up to the next whole unit. All right, so you tries for you, and that's what we'll start with tomorrow. You should be trying those things. See if you understand what's going to happen. There you go. 6.1 part 2.